Hello. So here we're going to talk about the geometry of linear systems. We have seen linear systems of equations uh, in the previous section. We saw the mad scientist problem, the cooler problem, the Carl's coins problem, and we saw that we had to have something that looked like this uh, to solve for the respective quantities, whether they were the amount of cheap bottles of water versus the expense bottles of water, and so on and so forth, right? So this thing is called a system of linear equations. It's in fact a 2 by 2 system. Why 2 by 2? Because it's two equations in two unknowns. In this case, the equation 1, the equation 2, and the two unknowns are x and y. And that's why it's called a 2 by 2 linear system. But we can interpret this system geometrically, and that interpretation can help elucidate for us whether or not a solution will exist, and we will be able to analyze systems like this. And at the very least, I want you to understand this geometric interpretation so that you can see so you can gain more intuitive insight into what's happening. Okay, so for example, as you can imagine, as you look at this, you can see, aha, this is the standard form of the equation of a line. This too is the standard form of an equation of a line. And so what we can see is that this causes us to have three different cases. The case number one, okay, is that this is my xy plane, let's say, and I have one line like this. Let's say this is L1. Let's let L1 represent this first equation, and let's let L2 represent this equation. If L2 is like this, okay, then there will be a unique solution because the two lines will intersect in that one point. So this is a unique solution. There is also the possibility, let's say this is my xy axis, that it could be that L1 is like this, and that L2 is like this. That would be no solution in the case when the two lines are parallel. Okay? Right? And of course, we remember parallel means same slope. Okay? So we'll be able to evaluate whether or not a system, whether or not the system's two equations represent lines with the same slope, and then we can determine whether or not it's likely that they either have no solution or, which is the final case that I'm about to show you, they have the solution set overlap when the two equations represent the same line. Okay, so that's the third case here. Okay, it's like this. Let's say this is x, this is my y-axis, and let's say that this line represents L1 and L2. In other words, that L1 and L2 represent the same line. Okay. So these are basically, and so this would be known as the infinitely many solutions. The infinitely many solutions case. And so having discussed this now, what I want you to realize is that just interpreting this system of equations in terms of lines allows us to gain some insight into what's really happening when we're solving an equation, system of equations, into what's really happening when we're solving a system of equations. This is a unique solution because it's the only point that makes both equations true, which we saw was necessary to solve the systems of equations in the previous section. This parallel situation, there are no points in common, so no point will exist which will satisfy both equations at the same time. And finally, this one, every point on the equation 1 is on equation 2 because they represent the same line. Okay? And so that then is the geometry of the linear systems. And And let me just briefly note that if the system is larger than this, like a 3x3 system or something like that, then basically it's planes instead of lines, so it's harder to visualize. But you can imagine like this, and you will see the intuition behind what's happening there as well. Thank you, and I'll see you again soon.